Yeah, myself, Dr. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study about the torsion. The course outcome and Bloom's taxonomy related to this session is course outcome number 6, and it is make use of the concept of torsion and buckling of thin shells, spheres, etc. to determine the stresses at various points of geometry. And the Bloom's taxonomy related to this topic is apply level. And let us begin with the torsion. What is the meaning of torsion? What is the significance of the torsion? An introduction of the torsion is here when a shaft is under a said to be in torsion when an equal and opposite torques applied at the ends. At the ends of the shaft, the torque is equal to the product of what is the torque? The torque is equal to the product of the force applied tangentially at the ends of the shaft and the radius of the shaft. So torque T equal to force times radius. That is F into R. This is the torque T. Now, due to the application of the torques at the ends, the shaft is subjected to a twisting movement. That twisting movement causes the shear stresses and the shear strains in the material of the shaft. Suppose if you are twisting, if there is a shaft, if you twist at the ends, if you apply the torque at the ends, what happens? The torque causes a twisting movement. The shaft is subjected to the twisting movement inside the layers. These layers causes the effect of this torque leads to develop shear stress and shear strains in the material of the shaft. So how to find out this torque experimentally is by torsion test rig. The torsion test rig is used to find out the torque of a material. So here one of the important, the torque is denoted by capital T and is the force times radius. What is the unit for torque? Unit for torque T equal to unit for torque T is Newton meter or Newton millimeter. Now, in order to, when the twisting movement occurs, the developing of shear stress and shear strains, from that how to calculate, how to derive the shear stress produced in a circular torque or the simple shear stress formula. So here, when we are going to consider here, there are in figure 1, the shaft, it is like one end is fixed, another end is free. With the before torque applied, T applied, here the layers fixed and AA. This is the AA fixed and BB is free and CD is the layer. In order to understand one of the marked here on that, the cross section of the shaft here, it is the circular cross section. And we are considering certain parameters which are coming to the picture in order to calculate the shear stress. So let R, capital R is the radius of the shaft, capital L is the length of the shaft, and capital T is torque applied at the end, BB, torque applied at the free end, and tau is the shear stress induced at the surface of the shaft due to the torque T, and whereas C is the modulus of rigidity of the material, it is the property of the material of the shaft. The modulus of rigidity is also denoted by capital G or capital N. Not only C, it is also capital G and capital N. Mostly standard books follows, some of the maximum books follows the capital G, but here it is not only C or G also you can follow. Now here, when a circular shaft is subject to a torsion, the shear stresses are set up in the material of the shaft. So to determine the magnitude of the shear stress at any point on the shaft, we consider the figure A, that is the shaft fixed at end at AA and free at BB section. And also there is a line at the outer surface of the shaft, that is assumed CD line. CD is the line assumed at the shaft, the fix at one end The CD is the line. Now, as a result of this torque, we applied the torsion, okay, twisting moment. The torsion is nothing but. Now here, as a result of the torque, the shaft end BB, this will rotate in clockwise direction. We apply clockwise direction, and at every cross section of the shaft will be subjected to shear stresses. The point D will be rotating here, will shifted to D dash, and hence the CD will be deflected to CD dash, which we will say here in figure B also, figure 2. Now, why here there is another type of torque also, twisting shear stress will be developed. When the force applied parallel to the cross section of the shaft, okay, that force is known as the shear force. That developed stresses by the shear force is known as shear stress. That also causes to shearing of the material. Now here, the due to twisting moment, rotation, fix and rotate. Okay, due to that also shear stresses and shear strains will be developed. So here the shear stresses and shear strains will be developed in this case study in an angular direction. That's why twisting moment and angle, the theta will come into the picture, because the rotation, the one is fixed and the other one is rotating. It causes the shear stresses will be developed. The rude example if you consider is a hand. If you twist, if one end is fixed here, one end is fixed, another end, if you twist this end, you can see that the real layers which will move in circular direction. It causes us those shear stresses and shear strains will be developed. So not only when the force applied parallel to the cross section of the shaft, and also if we apply the angular twisting movement, torque, if we apply twist, also shear takes place. That's why some of the materials we can remove, we can separate into two parts by rotating keep on. People will rotate. If the wire is there, the wire keep on rotate, then it causes due to shear stresses, it will be separated into two parts. And there is another motion that they will apply load here up and down, keep on up and down motion, then also shear stresses will be developed. But the point here is that due to twisting movement develops here the stresses inside the material. Now in the figure here, there are two things, the figure A and figure B. In figure 2 here, after applying the torque applied at the end B. So because of the B torque twisting movement, there is a layer, the CD becomes a CD dash. The angle with D dash, C and D is shear strain phi. And if you see in a front view, there is theta is also angle of twist. Here angle DO D dash is the angle of twist. This angle of twist can be observed in the side view along the cross section, whereas the shear strain applied on the surface, the shear strain. So here the position becomes DO D dash is the theta, and DC D dash is phi, that is the shear strain. The phi is the shear strain, theta is the angle of twist. Now let us derive, these are the considerations. Now the distortion at the outer surface due to torque T, the distortion at the outer surface due to the torque T, that is the distortion is a DD dash. This is a DD dash, okay, how to distortion, that is the shear strain at the outer surface, that equal to change in, what is the angle DD dash by tan phi equal to, what is the tan phi equal to DD dash by L, or tan phi equal to phi when angle is small, very small, that is a DD dash by L, that is the shear strain. The phi shear strain phi equal to DD dash by L. Now that is the outer surface. Now from figure 2b we can see, from figure 2b in this we can see what is the DD dash. DD dash equal to, if you suppose it is R theta, capital R, if you consider the radius of the shaft is capital R. What is the DD dash equal to R times theta? So DD dash equal to OD times that is R theta. So substituting this DD dash in the above equation of shear strain, then what happens here? Phi equal to DD dash by L. What is the DD dash? R theta by L. Phi equal to R theta by L. that is shear strain at the outer surface. Shear strain at the outer surface is R theta by L. We know the formula of shear strain by using from the shear stress modulus of rigidity versus shear strain. So now modulus of rigidity is C equal to shear stress by shear strain. From that shear strain phi equal to tau by C. Alright. Or C equal to, you can make it phi equal to tau by C. That is also okay. Then equate one and equate this both equations, shear strain and shear strain. Then what will happen here? Phi equal to tau by C. And another one is phi equal to R theta by L. Equate these two both the equations. Then what happens here? Tau by C equal to R times theta by L. Now C theta by L equal to tau by R. This the equation is observed here. C theta by L equal to tau by R. What is the tau here? The tau is here is the shear stress, where R is the radius of the shaft and C modulus of rigidity of the material, where theta is the angle of twist in radians, where L is the length of the shaft. So in this relation, this is one of the relation, tau by R equal to C theta by L. So what is the C here? The modulus of rigidity of the material of the shaft is given the shear stress induced by shear strain produced, or shear stress at the outer surface by shear strain at the outer surface. Now the shear stress at the outer surface and shear strain at the outer surface, that becomes here the equation C theta by L equal to tau by R. That is one of the relation. Now from the above equation, tau equal to R C theta by L. Now one more thing here, the shear strain, the shear stress also in proportional to the radius of the shaft. So what is that here? Now for a given shaft subjected to a given torque, capital T, the values of C, theta and L are constant here. In this equation, if we consider the equation 3, in this equation, R theta by R theta, C theta L are constant because the angular twist, modulus of rigidity of the material and the length of the shaft remains constant. But what is the variable here? Radius of the shaft. So tau is proportional to R and tau by R equal to constant. Then if the Q is the shear stress, actually is the tau is the shear stress here. For elemental shear stress, if we consider tau by R equal to Q by R. Now tau by R equal to, what is that here? Tau by R equal to C theta by L, we know. Now this is the tau by R equal to C theta by L, that equal to Q by R. This is the equation. It is clear that shear stresses at any point in the shaft is proportional to the distance of the point from the axis of the shaft. Hence the shear stress is maximum at the outer surface and it is zero at the axis of the shaft. So this is the basic derivation here, basic equation we calculated here. Okay, here that means here the shear stress, where Q is the shear stress, and also shear stress induced where at a radius, small radius R, and shear stress tau at the capital radius outer surface, that is a capital R. But it is how it is varying, tau by R equal to Q by R. This is varying. The variation of the shaft, here it is. Okay, generally here, now this is one of the equation, how it is, it shares, this equation indicates the shear variation of the shear stress in proportional to the radius or radial distance from point to point from the axis of the shaft, from distance of the point from the axis of the shaft. The shear stress is maximum at the outer surface because capital R is the maximum, and the shear stress is zero at the axis of the shaft. Now, what are the assumptions we considered here in this produced assumptions? What are the in deriving the shear stress in a circular shaft subjected to a torsion? So the assumptions we considered here is the material is uniform. The material of the shaft is uniform throughout. throughout the cross section here. The material of the shaft is uniform throughout the what? Throughout length and also cross section. And one more thing, the second assumption is that the twisting along the shaft is uniform. It is uniform twisting. There is no variation. That means linearity following. And one more important is that the shaft remains having circular cross section before twisting movement and after twisting movement, or before torque applied and after torque applied. The cross section of the shaft remains the same. Only circular cross section only. There is no reduction in cross section. Okay, the cross section of the shaft remains the same. It remains same after twisting and before twisting. And the fourth is that cross section of the shaft which are plane before twist remains plane after twist. The planes remains the same. And finally, the fifth assumption is that all radius which are in straight before twist remain straight after twist. So radius which are straight before twist and after twist, it is a straight. Radius lines are straight. There is no curved radial lines. That is the meaning in the cross section of the shaft. Now here these are the 5 assumptions are considered for deriving the shear stress produced of a circular cross section of a shaft subjected to torsion. This is the formula derived considered for a circular cross section of the shaft on here subjected to a torsion at the free end. And one more thing here, what is the maximum torque transmitted by a circular shaft? What is the maximum torque? In the figure 3 here, the maximum torque is considered when small r becomes a capital R. That means on the circumference of the circular cross section. So here the maximum shear stress induced at the outer surface of the shaft, and it is 0 at the center of the shaft. So a shaft is subject to a torque T, that is in figure 3. So tau is assumed as tau is considered the maximum shear stress induced at the outer surface, and capital R is the radius of the shaft, and Q is the shear stress at the radius of small r from the center. We are considering from the center is the reference point. At this radius, at this small r, the shear stress is Q. At a capital R, the shear stress is the tau. So at a capital R, the shear stress tau is known as the maximum shear stress. At a small r, the shear stress is the elemental shear stress. Okay, this is the ring considered here, elemental ring. Here the torque is varying radially. That's why we consider the cross section of the shaft. And here the circular ring. Now we will consider the shaft here, the shear stress at elemental level, and applies here from 0 to capital R. The integration part will apply for getting the total torque applied. Now we know the equation. What is the dA elemental area? 2 pi small r times dr. The 2 pi r, and this is the dr portion. 2 pi dr. Alright, 2 pi r dr dA. That is dA equal to elemental area equal to 2 pi r times dr. Now from equation 2, we know that already derived in the above equation, tau by r equal to q by r. From the q equal to tau by r times small r. Now that is the shear stress. What is the shear force? The shear force times radius, that comes a torque. Alright. The turning moment, that is the turning force, that is the shear stress into area q dA. What is the q? Tau into small r by capital R into dA 2 pi r times dr. That is tau by capital R 2 pi r square dr. Then after that what to do? Very simple. This 2 pi r square dr tau by r 2 pi r square dr. We want to torque. The torque at element level means what will happen? Turning force times radius. Multiply with this radius. Then it will come into here. So tau by r 2 pi r square into small r 2 pi r cube dr. This is the dt. So dt equal to tau by r times 2 by r cube dr. Now we want a total torque. Torque T equal to 0 to r dt. Here 0 to r tau by r times 2 pi r cube dr. Now tau by r 2 pi times 0 to r cube dr. Tau by r 2 pi This r cube dr means r power 4 by 4, 0 to r. Now substitute here after integration. In the place of capital R, it is 0. No need to substitute here. Substitute here capital R. That is r power 4 by 4. Now cancel it. R by 4 and r by, that is r cube times. That is 2 times pi by 2 r cube. Now tau times pi by 2. What is r equal to? D by 2. Substitute here in terms of diameter. Then what will happen? D by 2 whole cube, d cube. This 2 cube means 6. 16 times 2, 16. So tau times pi by 16 d cube. This is the torque. Tau equal to pi by 16 d cube. This is what derivation we have done for maximum torque. Okay. Now here, after this, the tau relation we got. Tau equal to pi by 16 times tau d cube. Okay. What is the unit of the torque here? The unit of the torque is Newton meters. Okay, pi by 16 tau. How we got it here? Newton meter or Newton millimeter here. You can simply substitute tau. That is a Newton per square meter. D meter cube here. D cube. Then that is becomes Newton meter or Newton millimeter. Alright. This is the torque unit. Now here, unit of torque is Newton millimeter. Unit of shear stress is Newton per square millimeter. A radius of the shaft is in millimeter. Modulus of rigidity C or G or N is Newton per square millimeter. Theta should be in radians. L should be in L is in millimeter. These are the units to maintain dimensional homogeneity. One has to follow dimensional homogeneity. Suppose if the torque is in Newton meter and substituting remaining Newton square millimeter or in millimeters, so it is absurd and it is highly contradictory to get the results. Results won't come. So we have to follow always dimensional homogeneity in engineering. Otherwise, for yielding the right results. Otherwise, wrong results will be yielded. Now here, these are the things we have done in this session. Let me summarize what are the things we have done here. We are following in this session. Okay. In this session, we covered what is the torsion, how the torque is applied, introduction to the torsion. The torsion, the shear stress can be generated in two methods. One is when the force is applied parallel to the cross section. Shear stresses will be developed, shear strength will be developed. That's what we have learned here. Where in the case of A, in order to derive the relationship of elastic constants, the elastic constants here we have applied. What is the here shear force applied parallel to the cross section, and the distortion takes place. This is the phi, the shear strain. Here in the case we have applied the force applied parallel to the cross section. Similarly here tangentially we have applied here. In twisting moment also, we apply the torque, will apply tangential to the cross section, and along the radius, then it happens a twisting moment. That causes the twisting moment. Here also twisting, motion, rotation took place, distortion. There is also shear strain. So in principle, both are here. The shear force has to be applied parallel to the cross section or tangential to the cross section. Then the shear stresses and shear strains will be developed in the material. So from the basic concepts we have derived in this session, the shear stresses, relation between shear stress and modulus of rigidity, angle of twist. That we have derived the relation of the shear stresses induced and developed in a circular shaft subjected to twisting moment. Okay. Now, one more thing that, and also we have derived here, one more thing is that tau equal to pi by 16 times, that is the maximum torque, tau equal to pi by 16 times d cube or pi by 16 times tau d cube. That is the torque, tau equal to pi by 16 times tau d cube. This is very important formula derived here. Suppose in the problem, how to apply in the problems. So find the torque of a when the shaft is subjected to a shear stress. find the torque when shaft is subjected to a shear stress, of 17 Newton per square millimeter, and the diameter of the shaft is, we consider here 15 millimeters, and assume that the modulus of rigidity of a material is 2 into 10 power 8 Newton per square millimeter. So how to solve the torque developed in this? So based on the given data, we have to approach different formulae related to the shear stress and shear strains. Now they did not give any shear strain, value of the shear strain, and also modulus of rigidity is not given. Yes, modulus rigidity value is given here. So now, based on the data given here, it is based on the given data, the shear stress of the material is 17. Shear stress developed here is tau equal to tau, that is 17 Newton per square millimeter, and the diameter of the shaft is 15 millimeters, and the modulus of rigidity is 2 into 10 power 8 Newton per square millimeter. Now here already all units are in homogeneity. Now what is the formula for torque related to this data? That is pi by 16 times tau d cube. Here the diameter is d, small d I considered here. That is the small diameter of the shaft here. You can make it as a capital D, that is 15 millimeters. Now substitute here tau equal to pi by 16 times tau, 17 into d, 15 cube. We will get the value of the torque developed in the units of Newton millimeters. Because all values, all parameters are in terms of is newtons and millimeters. That's why the output will come, the torque value is in terms of Newton millimeters. Suppose here, if you observe, what is the modulus of rigidity value we did not use in the formula. That means this extra data is given. So the required data for this considering the torque is the shear stress and the radius. From the shear stress and the radius or diameter of the shaft, then we can go for the torque calculation. Now we can also understand that torque is dependent on two parameters. One is the value of the shear stress, and the other one is the radius of the shaft or the diameter of the shaft. Okay, so based on the torque value is dependent on shear stress, value of the shear stress, and the diameter of the shear stress. All right, and the torque, one more thing is that the pi by 16 is the constant. Suppose radius of the shaft, here the shear stress depended on what? And one more thing, the shear stress also, the torque also depended on, in the formula of torque T equal to, as a twisting moment is considered, torque T equal to force times radius we have studied. Here torque is dependent on what? Force and radius. Now here I said shear stress and radius and diameter. What is the meaning here? That means shear stress involves the shear force. So, and also D involves what? D is, or radius is inside. So again the meaning is that both meanings are the torque depends upon the shear force and the radius of the shaft, or shear stress and the diameter of the shaft, both are same. Point is that ultimately depends upon shear force and the radius of the shaft. There is a torque dependent upon these two things. So the unit also remains same. Now in this manner you can calculate the maximum torque developed. That is what we have calculated, the total torque integration. Now one more thing, what we have applied here is that integration. First we went for elemental torque, then we applied 0 to maximum maximum radius, that is 0 to capital R. Then we integrated it, and after integration derived the formula of torque developed. That is the total turning moment or total torque. The total torque capital T equal to pi by 16 times tau dq. Alright, this is what we have calculated in this session.
Like, share and subscribe. Hit the bell icon for more updates.